Hello everyone, welcome back to this lecture 5. This is second lecture of module 2 and fifth lecture of this particular course. So here referring back to the basic properties of the electromagnetic wave. So here you can see that the fundamental properties of an electromagnetic wave, including its sinusoidal nature, perpendicular fields, wavelength and direction of propagation is explained in this particular image, right. The overall direction of the electric field does not change with time. So, it only shifts the wave in time. So, that it will be very clear from this animation if you see how the electric and magnetic fields are present here and how the waves are moving from one place to another, and this electric field does not change with time, it only shifts the wave in time, right. So, that is very important. So, it is basically the Maxwell equation that describes the generation of time varying electric and magnetic fields and the propagation of light as electromagnetic waves. So, this is the basic of remote sensing, and particularly for microwave remote sensing, you need to understand how the waves are generated, what are the different fields, how we are utilizing them in microwave remote sensing. Starting with the polarimetry, this polar means polarization, metry means measure. So, basically we are measuring the polarization, right, that is polarimetry. Polarimetry deals with the vector nature of the electromagnetic wave. So, this vector nature is very important. Polarization, that is the orientation of electric field vector as the wave propagates perpendicular to mutually orthogonal, that means perpendicular electric and magnetic field. If you remember the video, the polarimetry is a technique that is widely used in various scientific and technological fields from material science to astrophysics to study the polarization properties of the wave including light. Polarization is a fundamental characteristic of wave. This is the fundamental property, right, polarization. So, it describes the oscillation of the electric field vector in a specific direction perpendicular to the direction of the wave propagation. Understanding the polarization of light is crucial for a wide range of applications such as laser cutting efficiency, optical manipulation of particles and defect detection in composite material. So, this is very widely used. The polarization or the polarimetry is widely used in different community and they are using it for different objectives. Light can be described as a transverse electromagnetic wave with oscillations of the electric and magnetic field perpendicular to the direction of propagation. So, that was very clear from the diagram. The polarization of the light refers to the specific orientation of the electric field vector, which can be linear, circular and elliptical. Now, here we are referring to the electric field vector, right, and it can be linear, circular and elliptical. Linear polarization, it occurs when the electric field oscillates in a single direction, while circular polarization involves the electric field rotation around the direction of the propagation. Now, elliptical polarization is a combination of linear and circular polarization. So, this is both, where the electric field traces an elliptical path. So, this is elliptical path, but this is a combination of linear and circular polarization. Several methods can be used to generate polarization light or the polarized light, including the use of polarizing filter that was very common in our microscope, birefringent materials and the inherent polarization properties of certain light sources such as laser, right. So, these are used to get the polarization of the light, and now we will understand how it is being used in microwave remote sensing. So, in this particular slide you can see how the wave is propagating, right. Now, once you put the filter, right. So, this is the axis of polarizer parallel to horizontal, this is H, right. So, what will happen? Resultant will be like this. So, you are removing one field, right. So, this is the horizontal component, this is the propagation direction, and this is vertical component, right. So, this is what I was mentioning, linear, circular and elliptical. Here you can see the linear polarization, how it is behaving, the circular one and the elliptical one, right, in x, y and z direction. Based on the parameter describing the polarization state of a wave, there are three canonical polarization states. Here you can see for the linear, circular and elliptical polarization, what are the different properties we have, right. And this table has the parameter right handed circular polarization, left handed circular polarization, how it is different from each other. So, in microwave remote sensing, the polarization of the radiation is also important. So, those were the basics of the polarization, so that you will understand how a wave is behaving and how we are having a filter to polarize the light, or the polarizer we are using to polarize or use a specific field of the light. Polarization refers to the orientation of the electric field. Most radars are designed to transmit microwave radiation either horizontally polarized or vertically polarized. So, here we will be using H, or here we will be using V, right. So, here you can see this is one is horizontal and another one is vertical. So, this kind of orientation of the electric field is being used in the microwave remote sensing. The combination of polarizations are also used in microwave remote sensing. HH, which is horizontal transmit and horizontal receive, VV, the vertical transmit and the vertical receive, HV, horizontal transmit and vertical receive, and the last one, which is the combination of VH, the vertical transmit and horizontal receive. So, you will see these details in the subsequent figures, and you will be able to understand what I mean by HH, VV, HV and VH. So, here you divide these words HH, VV, HV, VH. So, the first letter of this defines the transmitter, this is the receiver. So, this is the transmitter and the right hand side it is the receiver. So, horizontal transmit, horizontal receive. The last two combination HV and VH, these two, right, HV and VH, these are referred to as cross polarized, because the transmitted or received polarization are opposite of one another. So, here you can see these are the planes orthogonal with respect to the propagation direction, and this is the electric field, right, here and here, and these are the axes, so that you will have the perception of 3D, right. So, this is H, horizontally polarized, this is vertically polarized. Polarimetry is the science of acquiring, processing and analyzing the polarization state of an electromagnetic field. Here HH, that means the first one is the transmitter and this one is the receiver. So, here HV horizontally sent and measured in vertical direction. This is VV and this is VH. Here you have vertical polarized light is being sent and the horizontal is received. So, this is called like polarized HH and VV, and this is called cross polarized, you have HV and VH. So, cross means both are sent in different direction. This is the example of polarization. So, this is HH, this is VV and this is HV, and this is the combination or the color composite of these three. So, here you see if we have HH or if we have VV or if we have HV, what different information we are having for the topography. Now here you can see in this particular HV, this particular area does not have any information. It looks like completely black, right? When we refer to VV, this particular area is showing the topography, right? You can see the details here. When we refer to HH, again we are having this information. So depending upon what is the objective of our observation, what is the objective of that space mission, you have to select the wavelength and the polarization, because the polarization will be mentioned in which wavelength it is measuring and whether it is HV, VV or VH, right. So those informations are available in your space agency website that you can refer. This is just for one example. Here you can see the CSAT satellite. In case of CSAT satellite, this is launched in June 1978. The frequency is 1.275, wavelength is 23.5, resolution is 25 meter, swath is 100 kilometers, swath is the width of the photograph, right. So this is swath. Look angle is 23 degree, polarization is HH and the look is 4. We will discuss this look in the subsequent slide. When we go with the ERS or JERS or radar sat, SERC, NVSAT, radar sat 2, you will find how this polarization is changing, right. So depending upon your objective, you have to select wisely which particular satellite image or which particular sensor is more applicable for your study. So this is the different modes of imaging. So here in microwave, either you will have the strip or you will have ScanSAR, spotlight, pulsar, INSAR or ISAR. This kind of measurement or the imaging modes are available. So depending upon the modes, you will have different information. So here you have strip mode, this is ScanSAR and this is spotlight. I hope the figure itself is sufficient to explain what we mean by strip mode, what we mean by ScanSAR and what is spotlight, right. Now we will talk about the side looking radar system operation. So here we have a sensor which is operating in this particular area with microwave remote sensing sensor, and this is illuminating the area with the radar pulses, and this is on board in this particular aircraft, right. So the signal is being sent. Now you see the house is interacting first because this is a side looking radar system. So this does not necessarily depends upon the height of the object. This is the position of the sensor and how it is looking at the ground. So now you see this particular house has started giving back the back scattering signal. Now this has interacted. Now this will start sending the signal, right. So here we have two information, one is time, another one is back scattering. Now we have two different types of imaging radar. So the side looking airborne radar, we have real aperture radar. So real aperture radar and the synthetic aperture radar, these are the two different types of imaging radar system. The real aperture radar, which is RAR, aperture means antenna and the real mean real or fixed length of the antenna. For example, 1 to 15 meter of the length of the antenna itself. Synthetic aperture radar, the name itself is synthetic aperture. That means the synthesized length of the antenna. So 1 meter antenna can be synthesized electronically into 600 meter synthetic length, commonly used in airborne and the spaceborne radar system, because if you keep 15 meter or let's say if you have 11 meter of the fixed antenna length, that will work as a 15 kilometer antenna length. So that much is not feasible to send in the space. So what we do is we use the synthetic aperture radar technique to synthesize the length of the antenna and measure the back scattering information. The distance between the transmitter and the reflecting object can be estimated using the measured signal echoes. Since the energy propagates with the velocity of light c, the slant range SR to any object can be identified or measured using this Ct by 2, where the time incorporated in the equation is divided by 2. Here you can see the time is divided by 2 because time measures for the pulse to travel both the distance to and fro from the target. Factor 2 is used in the equation. So, range that is used for the distance. In microwave remote sensing, you will always find the range resolution or range in many places. So, whenever range comes, it is basically the distance, right. So, sensor slant range, you see this is the aircraft, here you have the sensor, and perpendicular to the ground, this is the nadir, this is the flight direction, this is the horizontal plane, and this is the zenith, right. This is looking at this particular area with some angle. So, this is called slant range, and this will be the image center because your image will be generated for this particular area. This will be your image center. Now, we will talk about the viewing geometry. So, with this I will end this lecture. We will continue this topic in the next lecture. Thank you. Thank you very much.